But when you move beyond 50 stories, now you are thinking of fairly tall buildings or super tall buildings. So super tall buildings, and this is the Twin Tower World Trade Center that collapsed due to the aircraft collision. And if I ask what is the area of each of these floors, then the answer is each floor had an area of 1 acre. Each floor had an area of 1 acre. And this is one of the tallest buildings, very efficient building. And it was originally called the Sears Tower, and then it was renamed Willis Tower. And this is a masterpiece by this particular engineer. And he was born in 1929. He died at the age of 53, but he is considered as a very good engineer. He is called Khan, Huslar Rahman Khan, who was born in North India, the eastern side, that we call Bangladesh today. But in 1929, they did not have a Bangladesh. It was part of India. So this is a building, very nice building, and it is out of tubes. So it is out of tubes, and we call it bundle tube concept. And Khan invented this bundle tube concept by looking at bamboos. And he looked at bundled bamboos, and he thought, okay, if I make the outer periphery of bamboos, the building strong, then I can have a strong building. So he use that. And then they added an observation deck, and that is called ledge. And you can actually go there and see about 1,500 feet below. And then this Burj Khalifa, again, they have used very special truss arrangement in addition to massive columns to stabilize the building, and stabilizing the building is always a problem when it is too tall. And although it's 860 meters tall, you will see that, above 640 meters, there's no habitable space. And one of the problems with all these buildings is they are massive in the ground level, but they become smaller and smaller and smaller as they go up. That means, you have massive area in the ground level, but the areas become smaller. That is not a very good thing, because you spend a lot of money but you don't get much space. So this is Khan. He was born here in in northern part of India. He was born here, and we have a special relationship to this part of India, and that is the King Vijay came from that part of India. So the language he spoke was Bengali, and 50% of the words of that language is out of Sanskrit, and most of those Sanskrit words are exactly the same as the Sanskrit words of formal Sinhala that we use here. And because Sinhala is a combination of the language, the Bengali language, and the language that the people in Sri Lanka spoke. So we have in our formal Sinhala, we have a lot of Sanskrit words, and those Sanskrit words are exactly same as the Sanskrit words that they use in Bengali language, which we have about 50% of the language is those original words. So one of the biggest problems with all these buildings is movement. And this is, the people who are actually reporting about the traffic condition by staying in the 103rd story of this building, but they have a big problem. In a very windy day, the top of the building sways as much as 6 inches, the microphone sings back and forth, and people feel dizzy. So it is a problem. Then again, we look at another building. Everywhere in the world, they always use very smooth facades, and building movement is a massive problem. And in this particular building called Crown Resort in Australia, Sydney, Australia, which is designed by a Sri Lankan engineer. Sri Lankan engineer is designed by Dr. Dhammika Maharaji. He did BSc at Borotu in 1997. And he did PhD at Queensland University of Technology under the supervision of Professor Mahendran in 2003. He completed in 2003. Then he worked doing research, and then he worked under Mr. Nimal Perera, one of the greatest engineers in Australia, again a Sri Lankan. And then he became a master of the game. And then he designed the 120-story tallest building in Malaysia. And then he has designed this particular very complicated building in Sydney, Australia. And even today he is involved in two buildings. One is having 45 floors and another having 60 floors. And he is considered as the brain of the company of their Brisbane branch. It's a big company called Robert Bird Partners, owned by a Singaporean government. And in this building, to stabilize the building, they use some tuned mass damper. And the cost of tuned mass damper was 40 million Australian dollars. And 40 million Australian dollars is about 6 billion rupees. So you can see, to make the buildings work, they spend a lot of money. And this tuned mass damper was designed by RWDI of Canada. And they also have a branch in India. And when we want to do all kinds of wind tunnel testing, we go to them. And RWDI is the wind tunnel testing company because it's set up by 4 greatest wind engineers of the world: Rowan, Williams, Davis, and Irving. So it is the company for wind tunnel testing. Australians go for that, and in Sri Lanka also we go for that. And 77-story twin tower by Mr. Nuance Enaka, he used RWDI. And then Altair also tested by RWDI, and they do this kind of wind tunnel testing. And one of the features of all these buildings is they are having smooth facades and streamlined flow and vortex shedding problems. And then we are starting to see special buildings, and this is one of the special buildings in Sydney, located close to that particular tower. And if you look at this particular building also, it's a very special building because they are having not smooth facades, they are having very rough facades. So if you want to defy the wind, rough facade is the rule. And you can see it's rough. And the wind comes from this direction, it's rough. And when the wind comes in the other direction, it's okay because building is very stiff, no movement of the building. So Altair is a very stable building, although it's a very tall building and also inclined building, very special shape, but still it's a very, very, very stable building. So to overcome all these effects, we have to create turbulence. So we came up with a new model. And in our new model, what we have is, we are going to have a double facade. And double facade, I'll look at this particular building. We are going to have a facade here with handrails and then vertical columns at 2.4 meters, and then the handrail, the wall, parapet wall, the handrails, and then again we are going to fill that area with glass, laminated glass. You will ask why. The idea is, we want to have a facade so that no kid will have a chance of being blown away. And also we want to make sure that all these areas are protected, but we allow wind to leak. So when the wind is leaking, can wind exert forces? No. And in addition to that, we have columns like this, beams, facades. Why? We want to have lightning protection. When you have steel cage, we have a Faraday's cage. So the other idea is to create a Faraday's cage by having precast floating columns. And these are floating columns, and the floating columns, the walls, and again to create turbulence, we don't mount it at the front of the column, we mount the panel at the back of the wall, back of the column. So the idea is create as much roughness as possible and which roughness you can prevent water shedding effect. And then we can have any kind of arrangement with a dual facade, and then you will find, because you are protected here, you can easily have a simple wall arrangement, like large openings and so on, and you don't have any danger of being affected by wind. And then you'll ask why this type of arrangement has not been used, because this is a very good arrangement for tropical climatic conditions, but may not be a very good arrangement for cold climatic conditions. But on the other hand, you might think, okay, we can do various modifications and adopt the same thing for cold climatic conditions as well. And we have researchers already working on it, and Dr. Dhammika Maharaj is also working closely with us. And then, we'll not have straight balconies, we'll have twisting balconies. That means the projection of the balcony from the building will be a big value at one end, a small value at the other end. So building will look like twisted like this. And then Dr. Maharaj created the E-types model by using variable odd-shaped balconies. So all these are odd-shaped balconies rather than uniform-shaped balconies, and he created a 60-story building like this. And after creating all this 60-story building with scores at these levels, he said the load under each of these columns will be about 90,000 kilonewtons. So because of that, we have to expect something like 100,000 kilonewtons. And based on that, we proposed having 1.8 or 2 meter diameter piles under each column. And then you will ask, how about the spacing? These column spacings are about 9 meters, 10 meters. So there will be plenty of space for having four large diameter piles. And then again, you'll see, when you have such large diameter piles, it's not possible to maintain these basic rules like T times diameters. So generally, you have to go for something like 2 to 2.5 times diameters as the spacing between two massive piles. And so generally you will keep a distance of about 2 meters between two piles, because the diameter of the pile is 2 meters. So you'll see the basic rules that are followed by many engineers for small diameter piles are no longer applicable to large diameter piles. And if you ask an expert like Dr. Nalin, and he might say, keep a spacing of at least 1.5 meters to avoid one pile drilling, damaging the other pile. And so if you keep 2 times diameters with 2 meter piles, then again you'll see, by maintaining 2 times diameters as the spacing, you can still keep 2 meter spacing between 2 adjacent piles, and that would be sufficient to ensure the drilling of one pile not damaging the already completed other pile. Because we are using high strength concrete, the chances of such damage is also less, because we will be using very high quality cutting tools to create piles. So then, how about the partition materials in these walls, in these apartments? Do we have to use very expensive partition materials, or can we go for waste-based partition materials? So my idea is, no need to use very special ones, because already we are having a facade protecting the building, and then all the others are double facades, or the facade after a facade. So that means no need to have very strong materials, but you can use this kind of waste-based lightweight materials, but they are very strong materials. They are stronger than bricks and blocks, and you can see the load bearing, the way that these have been used for load bearing. And then we have tested them with proper load testing, and you can see they are very strong materials. And this particular house was constructed in 20 days. 2-story house completed in 20 days. So that's the advantage of all these new materials, and these materials are manufactured by the large factory of Mr. Niranjan Fernando, who is having huge wealth, because he has gone into the manufacturing based on waste materials. So there are many things that we can learn from all these. The main thing is, we have overcome one of the biggest problems of uh, uh, tall buildings. And here you can see this is the arrangement that you can easily use for 60-story building. Then how about 120-story building? What we do is we repeat this and create bundle tubes. Now this is one tube. Then what we do is we create additional tubes here, additional tubes around it. And by creating additional tubes, as they have done in Sears Tower, in Sears Tower you get additional tubes. And similar to Sears Tower, you can see there are tubes. So create additional tubes. Then we can even think of going for something like with nine tubes like that. We might be able to go for massive heights like 1 kilometer tall buildings or 800-meter tall buildings. But the difference between our 800-meter tall building and the Burj Khalifa is Burj Khalifa 800-meter height, it cannot be used, whereas our building can be used because it's not going to change its shape. It is the same shape, but the footprint can be about 2 acres. When you are thinking of something like 800-meter tall buildings, 8 acres, 2 acres or 3 acres, and in the lower part of the building, in these buildings, we no need to have the courtyard concept. We can have the complete building. So in the lower part of the building, all these can be the fully utilized floor, but as you go to the top part, you can have the center court. And then this one tube, create more tubes, and then you can go for taller buildings. That is the concept. And then to do all these things, we have very good foundation material, and it is rock. And Sri Lanka is an ideal country for very tall buildings because we have the ideal foundation material. And if you try to do a foundation in any other country, you might spend about 3 times the foundation that you spend in Sri Lanka. If you are doing a foundation in Thailand, the cost, or Malaysia even, the cost can be 3 to 4 times the cost that you have to incur for the foundation that you do in Sri Lanka. So Sri Lanka has very favorable conditions, and if we go for tall buildings with very cost-effective structures, we might be able to sell our apartments in tall buildings to many people, and especially those who migrated from our country might consider buying apartments for something like 100,000 Australian dollars or 80,000 Australian dollars, because to buy a house in Australia, they need at least 300,000 to 600,000 Australian dollars, depending on the location, and in some places they need even 1 million Australian dollars. So buying a house, apartment for 100,000 Australian dollars in a building where there are a lot of shopping malls and all kinds of facilities will be very attractive for them. And we are in a position to create huge business in this way. And at a moment where Sri Lanka is facing dollar crisis, this might be one of the ways that we can come out of the mess. And the other way is organic farming, where if we can say all our food is certified as organic, we might be able to sell most of our produce to other countries at a premium price, and then again come out of the mess. So we have to think of all these things. And then not only that, sometimes we have to see, are these Eurocodes sufficient? But again, you will see the Eurocodes have certain limits, like the maximum cube strength is 105 megapascal. And sometimes when you go for super tall buildings, you might have to use concrete having 150 megapascal. And then you'll ask, can we make 150 megapascal concrete? The answer is yes, and we are now running research projects. And Mr. Nandana today indicated that there's a good possibility of sponsoring one of the students who is going to look at the 120 to 150 megapascal range. And we have one scientist, Mr. Ravi Nissanka, who is manufacturing all these very special admixtures in Sri Lanka. So with all these things, we are in a position to do many things in Sri Lanka, and also we are in a position to go for super tall buildings if the need arises. But and we have the support collaborations from Australia as well, with the top designers of Australia working very closely with us. So they will be doing the designs and we'll be checking. So which means any investor who is willing to go for tall buildings in Sri Lanka, they have a massive opportunity because the local knowledge is available, materials are available, and alternative materials are available. So there are great opportunities for all the investors who are willing to invest in Sri Lanka because there's a ready market with a huge population who have already migrated out of Sri Lanka, who are aging, and they might consider, rather than staying in a cold country that they are not very familiar, they would be much better off living in warm country like Sri Lanka in very comfortable apartments and using their dollar pensions, converting to rupees, and using those rupees to live in Sri Lanka can again make it very attractive proposition to live in Sri Lanka in their retirement. And with that, we will be able to generate a lot of business in this country if we can improve the transportation system. And for that also, we are now in the process of working out the possibility of, manufacturing trains in Sri Lanka or making trains in Sri Lanka rather than importing. And our initial studies show we can make a train for 120 million rupees, whereas the imported one will cost 600 million rupees. So likewise, if we start doing things our way with our own resources in Sri Lanka has a great opportunity to come out of the current economic hardships created by various unplanned developments in the earlier days and also COVID situation that prevailed in the last 2 weeks. So with that, I would like to conclude, and the message is tall buildings are possible, and tall buildings offer many challenges, and then super tall buildings are also possible. But the difference between tall buildings and super tall buildings is in super tall buildings, we should not use transfer plates, whereas in tall buildings, we can use transfer plates. So that is the difference. So in super tall buildings, we have to make certain sacrifices in the lower floors because we are not supposed to use transfer plates. So we cannot optimize everything in a super tall building. Either the car park can be optimized or the apartment can be optimized. So we have to decide whether to optimize the apartment or the car park. But we should totally avoid transfer plates in super tall buildings. And also I have shown you how to minimize the wind effects, which means the super tall buildings can be designed for axial loads rather than lateral loads, which will make it very attractive to design super tall buildings in the range of 150 to 250 floor range or going up to about 1 kilometer, especially in locations where we like to have so many people living with all kind of buildings with so many facilities like gymnasiums, walking tracks, supermarkets, food courts, everything in one building. And even you can have things like a school in the building, because in the low part of the building you don't need to have a courtyard concept, whereas in the top part of the building you can have the courtyard concept to provide adequate lighting for apartments. So with that, I wish to conclude. Thank you very much for your attention, and I hope you would have got some questions. And I would like to hand this over to Mr. Nandana after the acknowledgement. And I have to thank so many, and I have written so many names: Professor Chris Burgoyne, Professor Calladine, all the staff of Cambridge University, and my friends when I was a student, a PhD student at Cambridge, like Professor Alan Khan. All of them are now professors, and some are deans. And Professor Ahmad, Professor Tim Mayabel, who was our former external examiner, Professor Campbell Middleton, our current external examiner, Professor Alan Khan, who can be an external examiner for one of our engineering faculties. He is the Deputy Head Cardiff. Professor Simon Gust, Head of Department of Cambridge University, and so many at Cambridge University. And then the staff at Morato University who helped us in so many ways, funded our research and so on. And then special thank for all the staff of Bath University who helped us to do a lot of research with Bath University, and also Professor Mahen Mahendran, who helped me when I was in Australia in 2003, and also again in 2018 for 2 months. So we have so many friends in Australia and also so many students in Australia. So we work very closely with them. Thank you very much for all the help that they have extended, and also Professor Priyan Mendis and his team. So thank you very much, Professor Priyan, as well. So then the question time, and I would like to hand this over to Mr. Nandana and his team, because I think they have some kind of panel discussion scheduled.